Good morning and welcome to everyone. My name is Sabrina and I give you some information before starting. Your microphone will be turned off and if you have any questions, please write them on the chat box that you can find on the right side of your screen. You can write questions during the presentation if you need clarifications, and also at the end because we have some more time for questions. One last thing, the meeting will be recorded, so it will be available in the next few days. Okay, now we are ready to start, and I give the floor to Chiara Wolter for the presentation. Thank you very much.
Hello everybody, sorry, but I have just one little problem with the phone. Okay, now it should be ready to start. Let's see, can you hear me?
Yes.
Okay, great. Now I'm trying to share my screen. Okay. Chiara, I've missed the can you invite me again to share? I have not the windows. Okay, great. Okay, now I think you can see me. Okay, let's start. Welcome everybody. Now we are starting with the first webinar, and we will speak about the energy efficiency in buildings. Let's start from what is a house, what is a building. And this is mainly a place, a space, which have to keep the right conditions, climatic conditions, to make the human being feel well and comfortable. There are many elements which affect this well-being, and because the human being is quite comfortable in having more or less 20 degrees and more or less 50% relative humidity. So when outside there is the sun or there is the cold because of the winter and the temperatures are increasing or decreasing, the home, the building is there in order to permit to the human being to be comfortable and to live. Depending on the outer environment, the building is the outer element, the outer factors have a bigger or a scarcer impact on the building, but there is a lot of climatic condition you have to take into account in order to make the right decision about the building. So some buildings are exposed to wind or to sun, and some others are not. So you can, in different situations, make use of different conditions, energy sources, but also you have to protect your building from the energies and the elements you don't want to have into your building. In the building, in the inner space, the factors influencing the comfort level are mainly the temperature of the air, which, as we said before, it has to be about 20 degrees, and the humidity. Those are the two main factors, but we have also the impact of the thermal radiation coming from the light from the sun. When the sun is coming through the windows as light, as soon as he comes into contact with some materials, as the floor, for example, these materials, this connection between the light of the sun and the materials transform the light into thermal radiation, and this is one effect very important for the use of the heating and for the use of the sun. As another element influencing the comfort, we have the air. The speed of the air has a big influence on our perception of the temperature. So if we have to decide how fast the air coming into for the ventilation, for example, has to be introduced, we have to take into account that this has a big impact also on the well-being, on the comfort. So if the speed of the air is very high or is high, we have to increase the temperature to have the same comfort. There is another important factor influencing the perceived temperature, and this is the temperature of the surface. The surface of the walls we have out of us. So if the temperatures of the walls, of the external walls, the inner temperature of the inner surface is very low, the 20 degrees air temperature are not enough to make us feel well. So the perceived temperature is an average, is also influenced by the other factors, as for example the speed of the air, as said before, but it is mainly an average between the temperature of the surface of the inner wall and the temperature of the air. This is very important because if we know that by our feeling has to be about the perceived temperature about 18 degrees. So if we have 16 degrees on the inner wall, we have to take the temperature of the air to bring it to 20 degrees. If the inner surface of the wall has a higher temperature, we do not need to heat that much the air, but we can heat it to a lower degrees. So in this, this means that the measure that we have to use to make the inner temperature higher is to insulate the envelope. And then there is a static procedure. So if we have a good insulated envelope, the temperature here will be higher. This temperature of the air is what we have to provide through an heating system. So this is what we have, which has an impact on our running cost, on the operating of the building. So this is one reason why we have to have a real look into the status of the outer envelope. One word more about our comfort. As we will see afterwards, there is every time a matter of balance. And we will see the energy balance of a building, but we have to start from the balance of our thermal comfort. And we need to keep our body in a comfortable situation. We need to balance the heat we produce with our metabolic activities, and this is affected by the degree of activities, of muscular activities we are doing. If we are running, we are producing more heat than if we are sitting or sleeping, from the environmental conditions and from our body size. And all this heat generation has to be balanced by the heat losses we have through respiration, through radiation. We are radiating heat, through convection and conduction of the heat through our skin, and evaporation. If the rate of our losses is the same as the rate as our metabolic rate, we are in a quite comfortable situation. If we cannot, if our heat loss are not that much because we are wearing something too big, we feel very hot. And at the opposite, if the heat loss is very high because there is an outer temperature which is very low, we and our metabolic rate is not that fast, so we feel cold. This dynamic situation is the reason why we have to control and to have a real control on the situation of our building. Our building has some characteristics, and it means our building has a size, it's big or small, and has a form, and it can have a compact form or a very articulated form. To evaluate the energy performance and the energy aspects of a building, we have to know that this A to V ratio is the so-called form factor, has an impact on the capacity of the building to have big or small losses, thermal losses. It means if the envelope of the building, which is A, is very much, if A, the surface of the outer envelope, is bigger than the volume, we need to have a bigger insulation, because by a higher A to V ratio, the building is tendentially is losing more heat than a building which is bigger or is more compact. So if we have some norms defining some limits for a building, a new construction building, we have to know that a bigger or a compactor building is intrinsically more efficient than a smaller one, or one which have a more articulated shape. As said before, the building has the possibility to give us some comfort or not, and this is the graphs. We can see here is the temperature that we have in the air, and this is the surface temperature, I said before, and this is the area where we still have comfort or not comfort. And this temperature is very well linked to the U value of the building, of the wall. Now we will see what is the U value, but this is the capacity of the building to let the heat flow through. So we see here that if we have a low U value, here is K because it is an old graph, but now it's called U. And we see that by an insulated wall, we can guarantee a big a higher temperature of the surface, so the temperature of the air can still be lower and guarantees at the same time the same comfort. In a building, We have substantially a balance, and this is done by the losses that we have and the gains that we have. This is a very, very simplified balance. It's just to understand how it works in the building. And this simple equation does not take into account some physical and dynamical things which in the reality occurs. But this is a very simplified model. But also the modeling we will see afterwards are simplifying some factors. But the main factor which is not taken into account here is the thermal storage capability of the walls. But we will talk about this later. This is a quasi-statical analysis. So we have some impact which are the losses and some impact which are the gains. And this equation gives us the needs, the thermal needs of the building. The first and the main losses that we have are the losses by transmission. This means that the warmth, the heat that we have inside tends naturally to go outside if the outer temperature is lower than the one inside. And we have some transmission losses from the walls, the outer walls, and this is usually the main loss that we have, because it is also the larger element that makes a building. We have a transmission from the roof, and this is also usually a high amount, not because of the large part, because the roofs are in big buildings are not that big share of the outer envelope, but also because the heat tends to go up. So the temperature difference between the basement and outside is lower than the difference of temperature between the last floor and outside. So here the transmission is also higher. Then we have windows, which are a small part usually of the building, but they have a very high U value, so their capacity to transmit heat is very high, and or it is usually higher than one that's in the walls. Then actually the status of the development of the manufacturing of buildings and of windows are very high. And if 20 years ago a double glazed windows was characterized by a U value by 2 to 3 watt per kilowatt per watt hour and square meter, now we are used to install double glazed windows by a U value approximately by 1. So the technology development has made big progresses, and this is in some cases, it occurs that windows are very much better than the walls if by very old buildings or very bad standard, energy standard buildings. And this brings to a lot of problems, of course. But usually the windows are the building element which has the lower performance, the lower capability to struggle against the heat flow. And last but not least, the cellar floor is transmitting heat to outside. Normally, this transmission is lower because the temperature of the cellar floor or to the soil is not the same as the outer temperature. So the temperature difference is lower and the transmission is also lower. The other bigger element which constitutes the losses is the ventilation. The ventilation is needed normally or substantially to guarantee that the quality of the air is enough and that we have enough oxygen and all CO2 and all the toxic component in the air coming from furniture or from uses of the building. They can be put outside and the quality of the air is guaranteed. This is the very objective, the very aim of the ventilation. But it happens very often that the ventilation is used as a regulation for the heat, for the temperature of the room. And this is the cause. This is why some in older buildings the share of the ventilation on the losses is very high. At the other side of the balance that we have seen before, no, this one too much. Oh no, okay. Yes, just to recap, the thermal transfer can occur as a thermal conductivity, as a thermal radiation, as a thermal convection. And in the materials of the building, the element of the building, the very important characteristic is the thermal conductivity of the elements. This is the so-called lambda factor, and this is very, it depends on the density of the material. A material which is very compact, which has a very specific, a higher specific weight, has a very high lambda, and a light materials which has very much air inside. It's a material with a low lambda value, and it is a good material for the insulation. As we see, the value, the lambda value, it's a characteristic of the material of the air, is 25 times lower than of water. So water has the possibility to bring heat within himself very much higher than the air. And so it's also by the building elements. If you have a very warm heavy wall, it has the capability to transmit and to bring heat outside very higher than a lighter wall that is constructed by wooden, perhaps, and not by stone. If we see, this is a section of the wall. We see that inside we have an internal plaster, we have a brickwork, and then we have some insulating materials and the outside plaster. We see here in this graphic that describes the proportion of the insulation effect between all these materials. We see that the 12 centimeters of insulating materials have 80% of the effect of the insulation effect respect of the other parts of the wall, which are very, very heavy. So the capability of this panel is done by the presence of the air inside. Air which cannot move, so it's not so simple for the heat to go outside. At the opposite part of the balance, we have not only the losses, but we have also the gains. So the gains are done by, first of all, solar gains, which is the energy coming from the sun, mainly through the windows, because as said before, the light from the sun, once gone through the windows, once gone through the glass, is transformed in thermal radiation. This has a contribution to the heating of a space, of the closed space. But also from the other parts of the wall, which are not transparent, a little bit of solar gains has also some effect. But the main, the larger one is the solar coming through the windows and transforming itself in thermal radiation. But we have also other internal gains, and those are mainly by provided by the presence of people and all the devices are using electricity. Everyone knows that each use of electricity has a waste of heat in itself. So the most efficient have less loss, but we have an internal production of heat independently from the heating plant. All these losses and gains brought together are here listed, and here are the losses, so the heat going out through the windows, the heat loss by the walls, the heat loss from the ceiling, from the floor, and here the ventilation losses. All those losses together, put together, are here, and this is the quantity of energy that go outside of the building when we keep it to a certain temperature. And the gains, so the contribution from the outer and inner life, is represented here by these two yellow and violet lines. So the total gains, or the total losses minus the total gains, give us the quantity of heating we need to provide, to supply to the building in order to keep it at the 20 degrees we aim to. This quantity of heat that we have to provide is the energy demand of the building. And this energy demand is not only determined by the energy needs, so from the characteristic of the envelope, but also from the efficiency of the heating plant. At the first stage, it's very important to reduce the energy needs from the building, and afterwards it's important to increase the efficiency of the plant. But often it occurs the opposite, and often the first things which is first measure that is introduced in a building to be refurbished is the change of the heater. So if we make the best efficient plant or generator in the building, we have for sure a saving effect. But we have not, or we skip at the moment, the possibility to have a bigger results which comes from the insulation of the outer envelope. By the way, if we do first reduce the energy losses by integrating an insulation, we have the possibility to reduce also the size of the energy plant, so, or the generator. So we have a double economic impact because we have a bigger savings effect, but afterwards the expenses for the change of the heater are lower because we have to choose a lower size, a smaller heater. What is a heating system? A heating system is composed by three main elements: the generator, the heat sources, the distribution network, and the heat emitter. There is a fourth very important element, and this is the control. The regulation of this system, a good regulation, is very important to save, to make the plant working at its best. Each heating system uses a medium to transfer heat from the generation to the emission, and usually this medium is water, but it can be also air or steam. Steam generators are mainly used for industrial facilities, and air is mainly used in sport facilities. So the main air heater you find are in the sport facilities. But not only. But usually for the heating is water the main medium used. If we have these three elements building the heating circuit, we have the heat generation, we have the heat distribution, and we have the emission. To define the efficiency of the whole, we have to put together all the efficiency of all the elements. So it's not sufficient to have a very good heat generator if the distribution and the control and use are characterized by a very low efficiency, because as you may know, the final value, efficiency value, is done by the multiplication. That's the product. It's the multiplication between all those factors, and being all those factors less than 1, the final it is sufficient that one of those is very low, and the final results will be also very low. And this is, as I said before, the generation. This is the boiler. Then the pipes, distribution pipes, must filled by water, and the emission at the end. We start from the end, and the heat emitters are mainly 3 types. We have heaters, so-called radiators, but the main physical effect used by them is the convection. But these are the very typical, and they are in different materials: cast iron, aluminum, steel. They are really heavy, and they are very good to have to provide a heating which is very constant in the time. So if we have this type of emission, but we have one room we use 2 hours a week, these are not the very best emission that we have for this. A convective system like fan coil here is very much faster in heating, but it heats the air directly as just a convection, and has no radiative part in this heating. And at the opposite, we have radiators panels, floor panels. They can be mounted also on the ceiling and or behind the wall, behind the plaster. But those are using the radiation kind of transmission of heat transfer. So it's another, they heat the wall element, the building element, and the floor or the ceiling are re-emitting radiation, heating radiation into the room. Those are three different types of emission are characterized by different water temperatures. So the heaters here are normally driven by high temperature water. What does it mean? The temperature starts from the boiler at about 70 degrees and comes back to the boiler 50, 60 degrees. By the convective system, the temperature are quite below this, and it starts by 50, 60 degrees and comes back to the boiler to 40 degrees. And the radiator panels, they are operated by a very low temperature. They are the so-called low temperature emitters. And this means that the temperature can be by 35 degrees and comes back to the boiler by 25 degrees. So these are more or less the range, the temperature range that we have in these different heating types. The shape of the radiators of the heater has also an impact on the radiation and convection share. So you have seen here is typical just radiation, here is typical just convection, and those kind of heaters are using both type of heat transfer, radiation and convection. And this has an impact on the quality of the comfort, because the radiation has a possibility, let's say the opposite. The convection has the disadvantage that it moves the air, so that there is a lot of pollution in the inner pollution, which which is then transported through the building, and the radiation has not this effect. Then we have the distribution. So we have to take care that the efficiency of the emission is as good as we can, and then we have to look at the distribution. The distribution is very important because the water is heated by the boiler, and then it goes a very long way through the building. And if the pipes are running into the building, there is not a big problem to have. It's just as we have one more emitter if we do not insulate the pipes. But if the pipes are running into the cellar room, perhaps, or into the roof, which are not, which are spaces not used usually, we are having big losses, big distribution losses that we have to avoid. There is also some particular cases where two buildings are both supplied by the same boiler, and sometimes the distribution pipes are going outside before going again into the building. And if those points, those weak points, are not very well designed, the possibility to have very big losses is very high. And once the plant starts to work, it's not that easy to make some refurbishment. So it's very important to have one look on designing look on this, but also if there is any refurbishment measure, this is really a part which can lead to 30% of losses, just itself, the pipes. The last one, and one of the only one with an efficiency which will be measured usually, is the generators. This one, it's a boiler. It's a representation of a boiler, and the efficiency of the generators is proved by test before selling it, and there is a lot of testing measures in order to increase the efficiency of the boiler. The other system elements are not so well tested, also because they are usually depending on the type of installation. This is a device coming from manufacturer, and it has to be as efficient as possible. What is efficiency? Efficiency is the relationship between how much fuel we do put into the boiler and how much heat is made available for heating purposes. So this is what we call energy efficiency of a boiler. Then we have losses. What's going on here inside? The burner is burning gases or oil or biomass, and here some water will be warmed and will be then put into the distribution pipes to the emitters. But during the firing, there is some heat who is going outside the boiler. If you have been in a thermal room, a technical room where a boiler is, you will see, there is very warm, and those are mainly the losses from the burner. And then we have also some loss coming through the outlet's gas. As you know, the gas coming out, they need first to be warmer, because if they are too cold, they do not go out to the chamber. But they have, but when they are going out, they are bringing out a lot of energy that we do not want to lose. So in order to reduce the losses of the boiler, some years ago, more than 20, it was introduced a condensing scheme. So here is the scheme of a normal boiler. You have the burner, and here the water going through the boiler, coming in cold or colder, and here the water will be heated, and then it goes out and go to the distribution. And the air from the combustion, from the burning process, go out with very high temperatures. The condensing boiler has put one step more, and after the burning gases before going out, they pass by in this the scheme, but they pass by and preheat the cold water coming into the boiler. So a first preheating is made here. So the water coming from back from the distribution pipework at coldest temperature comes here, right? And it meet the gases, the outlet gases. So if this temperature, the temperature of the water is low, it's lower than 60 degrees, the latent heat present in the gases condense, so it rains here inside, and in this condensing process, the heat will be transferred to the water. So in this step, we have the possibility to use a quantity of energy that usually in a normal boiler cannot be used because it's present as a latent heat. Only if the water coming here inside is very cold, is colder than 60 degrees, this step occurs and it rains, it's produces a lot of water, but it saves also a lot of energy. It's reused, and the temperature of the water here is higher than here, and is higher than here. What does it mean in terms of figures? We have at the left side a low temperature gas-fired boiler. This is a non-condensing boiler, and here we have a condensing boiler. And we see this 100%, which is normally used to define the energy efficiency of the heater, is based on the calorific value HU. This calorific value HU is defined as 100% of the energy we can have from fuel, excluding this additional usable condensation heat. And this accounts about, about 11%. So if you have a boiler which is very good and transform into heat 95% of the fuel, of the energy introduced, is a very good normal boiler. We are accounting this 55% on this part as 100%. We do not take into account this 11%. If we have a condensation, we can use this one because it's a condensing boiler is making exactly this, using the condensation heat which other boilers are not able to use. So we have the possibility, the theoretical possibility, to have 111%. And this is not, we are not producing, generating energy, but it's because the 100% is accounted on these partial figures, the calorific value HU. So here are listed all the losses that an usual gas-fired boiler has, and those are the heating. Here are the outlet gas losses and the radiation losses through the envelope of the boiler. And we have the same outlet gas losses, the radiation losses, but we can use this 11% more. And so the average efficiency of a condensing boiler is higher than 100%, which is against the thermal laws, but it's only because this is the 100%. And it was decided not to change the whole accounting system for all other boilers, and so this is the motivation why we have an efficiency which is higher than 100%. But as said before, this condensing, this 11% more that we can use, can be used also if the temperature of the water coming back from the heating system is lower than 60%. And the lower the temperature is, the more the condensing boiler is working good. And we can see it in this part. And if we have a condensing boiler, these two lines are the condensing boiler, and these two lines are a normal low temperature boiler. And if we have the differences in efficiency, if we have two temperature stage, high temperature and low temperature, those figures are the temperature of the water going heated by the boiler, and 70, for example, and this 50 is the temperature of the water coming back to the boiler. And if we operate the boiler at a lower temperature stage, 40, 30, for example, to feed some radiation panels, the efficiency of a normal boiler is not that different. It's a little bit different if the outer temperatures are really very cold, but by 0.5 degrees, the difference is not just 1-2 point efficiency. If we have a condensing boiler, the differences between a high temperature or a low temperature is very high. So if you have outside -5 degrees, a condensing boiler which has a distribution pipework with sprung with 70 degrees is 5–6% less efficient than a condensing boiler who is working with 40–30 degrees water. And this is very important. This is the reason why condensing boilers often are not very good used, and the people are expecting a very good saving from substituting a heater with a condensing heater, and at the end of the year they see there is no real saving, and this is because the temperatures were too high, and in the condensing boiler there was no condensing process. No condensing process, the 11% more that we could use cannot be touched. So it's just like a normal boiler. And now the energy balance is now split in input and output, and we see at the right side we have all the losses: manual ventilation, losses through windows and doors, losses through floor, through outer walls, through the roof, and heating losses also from the boiler. And at the left side we have all the input. So we have the passive solar we can use, the internal gains, and the rest has to be supplied by the heating. So for this building with 115 square meters and 40 square meters windows, it has a yearly consumption of about 250 kilowatt-hour per square meter a year, and we have to put a big part of this through heating, because the internal gains and the passive solar gains are not enough to cover any bigger share of this. We do now a bigger insulation of these windows and doors, floor, outer walls and roof, and we are switching from the manual ventilation. It means that we can open the windows for ventilating, so in order to increase the quality of the air, we switch to a mechanical ventilation. We see that this can be the result. The controlled ventilation reduced the loss through the air. The better insulated elements reduce the losses by transmission. Also, passive internal gains are reduced, not because as you said before, it was higher here, the figures. Those are smaller, not because there is cloudy weather, but because reducing the demand of the building, the needs of the building, is reduced also the part of the solar that we can provide, that we can really use. that means that if we have already reached 20 degrees and we have still the sun shining through the windows, we cannot account into the balance the energy used to increase the 20 degrees to 25 degrees. So this part of contribution from solar passive cannot be accounted. So this is why this amount is lower, is because we reach, thanks to a better insulation, we reach the aimed temperature much faster. So we have not to use, we cannot use the rest of the contribution of the solar, and the same is for the internal gains. In this refurbishment situation, the building is the same. We have about reduced more than 60% the consumption from 250 kilowatt hour to 100 kilowatt hour. And this is the aim we have thinking about energy efficiency in building, because we have to use to make some measures in order to increase the efficiency of the buildings. Because the main energy that we are using in existing building, in older existing building, is the energy which is transferred very faster into the outer surroundings. And to increase, to make some intervention, it's important to make an energy audit. The energy audit is the tool, the instrument we have to decide, to have a strategic plan for the refurbishment of a building. Through the energy audit, we try to describe, to replicate the behavior of the building through the year, and to calculate the savings that some hypothetical measure can bring. Once we have all the measures defined, we can choose which is we can choose which measures we can realize with several criteria. So we can say, I want to reduce the consumption of the building. I want this building to reach nearly zero emission building standard. So it doesn't matter what it costs. I want to reach this topic, this goal, or I have 100,000 euro to invest. What is the better measure I can choose in order to achieve some efficiency? But we can make different choices or different scenarios only if we have a clear idea on how the building is working and what he is consuming. The first step to have an energy audit, to start an energy audit, is to have some documentation. The first information we need are the information about the building, how big, the size, how it looks like, what it is used for. It's a home, it's a residential building, it's a commercial building, it's an office, because all the difference in use set different use profile or different needs. A commercial building has usually very low a domestic hot water consumption. A nursery or a kindergarten has usually a very high consumption of domestic hot water, just an example. And it's a very important data you have to start with is also the consumptions. And the consumptions, in order to make an energy audit, the consumptions have not to be just the bills, but you have to check if the bills are stating a real consumption or just an amount, a forfeiting amount. The existence of the real consumption data about 1 to 3 years, this is the better condition, enable us to make a real state of the art of the building. And this, with this few data, we can make a first pre-assessment. So we can say, okay, this is a building which consumes very much, very low, or is an average building. The data has to be from thermal and electrical consumptions, and then we have here all the values about how big is the building, how many floors, which is the A to V ratio, and so we have an idea. After having made the pre-assessment, it's crucial to have a good on-site visit. The visit on-site is very important because in many cases, for example, in schools, the people deciding if the building has to be refurbished are not the people who are using those buildings. So they can see this is an older building, this is a high consumption, or this is has a broken window, so we have to substitute it, or there is some, it rains through the roof, so we have to substitute it, but they do not have a very close idea on how the building is working. So the on-site visit enable us to gather information on the discomfort zones, where it is too cold, where it is too warm, in which rooms the heating does not work, or the ventilation does not work, or something like this. And this is the first investigation that that can give some important clue about the working of the building. On the on-site visit, it's a matter of dimensioning. So it's a check if the measures are of the drawings are okay, if how are the elements of the building, and what it is the status of the elements, if the plaster is broken, or if there is some other refurbishment needed, or the plant, it's an old plant, it's a new plant, it's the controlling thermovalves out there or something like this. And we can also use very important tools to investigate. Okay, photographies, pictures are really very important in order to catch some details that perhaps you don't see at the first glance, but you can look for them afterwards. But a real important or useful tool is instrument is the thermography. The thermography enable to see the to measure and to see the surface temperature of the building, and you can use it from inside and from outside. So here in the picture we see those are two pictures from inside, and it's clear how in the corner here it's a thermal bridge. It's a geometrical thermal bridge, but the effect is very important, and this is a real a weak point of the structure, because there is the possibility to have some spores, and this is for a school is not that good. And here you can see also from the construction of the wall, then there is a very irregular distribution, and that also in the here there are some holes which can increase the transmission and the losses, the heating losses. And here is a picture from outside, and where you can see this is probably a kitchen, and you see the hole for the ventilation for the kitchen, but you can see also that there is a heater behind this window or under the window, and here this is the distribution going through the whole building. And this is a typical building technique or building praxis that there is a niche under the window, and there this is the place where the heater find its place. And if the wall here is 30 centimeters in this normal average part, here under the window is usually 15, 12, and in this very place behind a very thin wall, there is the heater, and so the result is that the environment outside is very well heated. but inside. It's a big share of this heat which is lost into the surroundings. Here another case, and here you can see not only the heater behind the wall, but also in the, this is a garage, not closed garage, it's just a in the basement, it's open. So here, this is a kind of outer wall, but it has no particular insulation. So also here, the loss are very high. And here, just another typical picture. You can see all the losses from the structure. So those are the floors of each floor. And here this is concrete. And the concrete make heat transfer very high heat transfer. So here's another weak point of the facade. Those are all information you can gather during an on-site visit. And then when you go back, you can start with the modeling. So from all the information you have, you build a mathematical model. You can use several different software to do it. The main difference between them is if you want to have a semi-statical calculation or a dynamic calculation. A semi-statical calculation is it's a calculation done month by month with different climatic data and different needs. And in this model, it is very used if you have a consumption which is more during the cold season of the year and not during the warm part of the year. So in those situations, semi-statical model is quite good. If you have a very complex use or a very high cooling, aiuto, sorry, I have some problem. Just 1 minute.
Just a moment, we are trying to solve this problem and then we can start again. Okay, I think we have solved this problem, and just a moment for the new connection of Chiara. And if you have any question, please write on the chat box. Thank you.
Hello. Okay.
Okay, we can hear you now.
Okay, sorry for this, but I don't know what's going on. And I had to restart. Okay. The model. Once you have built up the model, you have to validate it. So you have to make a match between the real consumption you have and the weather consumption of the period you was using, the real weather consumption, and then and you have to make a match if the model works like with the results that you are expecting from it. Once you have a validated model, you can see some results, and you can see here are all the different components of the building, so the walls, the outer walls, the roof, the basement, the floor basement, the windows, the ventilation, and you have just a look on which are the responsible for the thermal loss that you have. And this is just a first indication on where it is better to have some intervention. Then you have to define some refurbishment. So you make several scenarios. When in the first one here there is a envelope insulation, windows substitution, roof insulation, heater substitution, boiler substitution, and here is also one on the lighting measures, and then some summarizing of them. And then you can see here in the building you have the single measure savings you can achieve, and the scenarios, the mixed scenarios. This is the first output from an audit that you have, and then you can see the results, what is the impact on the consumption, but then you have also a cost, and then you have to make a financial and economical analysis on if the measure you are introducing is good enough. And here you can have in the economical evaluation if you have some incentives, some subsidies, and then you can account the payback time, the simple payback time, and the payback time taking into account the incentives that you have. And this is then the valuation of the intervention from an economical point of view. If the measures are are good and they are advantageous, it's a possibility that you can eventually realize the interventions, and this is a very good. It's very important to have all the measuring before, so that after the intervention you can have a plan of monitoring and control, and you can time by time verify if the measure realized are good enough or are like you was expecting, or if they are better, or they are, if you have to make something more in order to reduce the consumption. And if you have the chance to make some confrontation, this is the wall before the intervention, and here is the wall after the intervention. So in this case, you can see the difference in the wall is very high. So I am ready with my presentation about the energy efficiency of the building. And I don't know if you have some question or some clarifying needs, I'll be happy to make you an answer. Okay, no question. I hope it was not that boring what I was telling you. And I don't know, I think we can close the session.
Yeah, okay. Thank you, Chiara. If there's no other question, if there's no question, we can conclude the meeting. And as I said, the recording of the presentation will be available soon for all partners of the project. And okay, thank you to everyone for coming, and goodbye.
Okay, thank you. Bye.